Okay, so before Patrick kind of takes us through a hands-on part for Cocos, I'm going to quickly walk through kind of Raja and the features that are provided with it. Raja is another programming abstraction layer, somewhat similar to Cocos, that's developed at LLNL along with the other labs. I work on the SYCL backend here at Argonne, and I'm Brian Homerding, your moderator for this session. So how does radasha provide performance portability? So it does it by being a C++ library. It enables you to write these portable single source kernels, and you basically recompile for whatever architecture you're targeting, whether it be the Xeon Phis on Theta or the NVIDIA GPUs on Theta GPU. The idea is to encapsulate the application source code from that underlying programming model that you're running with. So even though you're running a CUDA kernel, you're not going to see any CUDA code in your Raja application. And overall, the idea is we support a bunch of parallel patterns and we provide performance tuning options. Now I'm only going to be able to talk about a few of these today, just to kind of give you an idea of what Raja is capable of. I'd be happy to go into more detail on Slack or into a breakout room with people if there's interest. One thing to mention though is that Raja is an abstraction only over kernel execution. So it's kind of bring your own memory management. There's a related project Umpire that does memory, that abstracts over memory management, but Raja is really just focused on how you execute your kernels. So in Raja, loop execution has 4 core concepts. Okay, there's the execution template, the policy type, the iteration space, and the body. So as you see here, we have a Raja for all. That's the template type. Then their execution policy, which is the template parameter. This is kind of where the interesting stuff happens. This is saying how to execute this kernel. Then we have our iteration space. This can be something as simple as a regular range, like 0 to 10. It can even have like negative indexing or negative strides. And it can even just be an arbitrary list of indexes that you want to visit. And finally, we have a Lambda loop body, which is very similar to the way that Cocos captures the kernel. So this kind of interesting part, the template parameter is going to say how to execute this. So you have a variety of options. So on Theta GPU, you're going to want to execute with CUDA exec. This way you can control the block size. You can decide whether or not to execute it asynchronously, or you can use OpenMP threads on Theta. But to go into some of the more interesting use cases, I want to look at these nested loops, once you kind of get more complicated kernels happening. So essentially, this is what we're going to see. It's now a kernel. It's a Raja kernel instead of a Raja for all, just saying that there's a more complicated, it has multiple loops to it. And it has the same 4 basic concepts, except now instead of a single policy in space, we have several policies in several spaces. So the order of your policies and spaces match. So basically your column range is going to be your first parameter for the range, and your first parameter for the index is going to be your column also. And this is kind of what allows it to do the mapping through the templates. So here, the first parameter goes to 0, and that's how you kind of control it with this execution policy, which is the template parameter here. So 0 is going to be our inner loop. So our column, we're going to have the column be the inner loop and the rows be the outer loop. Now, as you might guess, this allows us to do some interesting transformations quite simply, like being able to swap the loops out. So the difference between these, it changes the order of the loop execution. So you swap the row loop from the outer loop to the inner loop just by swapping this kernel statement. The philosophy and the design for Raja is you can do this, but you don't have to actually touch your application code. So like your scientific kernel stays the same, you just change how to execute it. Another important thing we can do is loop tiling. So this is kind of a hand tiled up example. So you have your little kernel down here, and you have to add in a few extra loops, do some calculations, make sure you're not going off the end of the bounds of the tile before performing your execution. Now with Raja, you get some of this for free. So now we add in that we're going to do some tiling. This is all in our kernel policy. Again, this is going to be put somewhere separate from your actual kernel. So you map in these tiles to your 2 different indexes. And then you have your inner for loops. And Raja is going to take care of mapping the indexes and making sure nothing goes beyond its bounds. Another important thing is like thread local data. So far we kind of looked at these perfectly nested loops, but you can have kernels where there's some code that needs to execute in between one of the inner loops and the outer loops, like the matrix multiplication example we kind of saw earlier. So the idea is, okay, how do we want to capture this with Raja? So you can kind of create this complex kernel where you have multiple lambdas all getting executed. So you have your policy, then a lambda, and then an inner for loop, another policy, and your final lambda. And that's how we're going to kind of provide this control over the execution of this complex kernel without having to actually change the code inside of it. So to do this, we also want some thread private data or some thread local data. And that happens using the template kernel param. It's like kernel, except now you can pass in an additional tuple that'll have all your thread local data inside of it. And then each of your lambdas is going to have that as its next parameter. One thing to note here is that all your lambdas are going to have the same arguments. This is so that kind of Raja can do its template mapping for these different kernels. So even though we don't use anything inside here other than dot, we still need to pass it all into the lambda when we declare it. So this is kind of putting it all together. This is what your matrix multiplication Raja kernel is going to look like. So you notice here we still have our kernel policy to control it, right? And this is what we're going to need to. This ideally is the only thing that needs to change when you go to a new system. And the idea is to provide some control over it. So if we're on theta, we say we want to execute with OpenMP threads. So let's say we want to collapse those outer two loops. So we can use this statement collapse, providing it the OpenMP parallel collapse execution and the two arguments that are going to be collapsed. And then we provide our inner lambdas and we're going to execute that inner loop sequentially. Now when we go to theta GPU, we're going to execute it a little differently. We're not going to collapse anymore. We're going to instead put it in a kernel, CUDA kernel. And now we're going to take that first index, the rows, and we're going to map those to thread blocks. And then we want to have the inner loop, the columns, go to the actual threads inside of each block. And Raja, since we're doing it in a loop here, will take care of kind of any overlapping or not perfectly kind of mapping to the threads and blocks. So that's kind of a very quick overview of the type of things that Raja is capable of. You can find a lot more examples online through their GitHub. They have several different examples. There's various projects using it. The user guide is also online. And again, I'd be happy to answer any questions in Slack. But now I'm going to transfer back to Patrick, who's going to take us through some hands-on with Cocos.
Yeah, hi.